Okay, we just introduced how to develop a neural network to do the regression model. Means we want to learn how to map this input x to a continuous value. Usually when we deal with real-world data, it's impossible to successfully train a neural network at the first try. So usually we have to go through a debug process. So it's very important to understand this neural network training recipe. Here I borrow the lecture note from Li Hongyi. Okay, the part shown in red rectangular is define a neural network loss function and perform gradient descent to find the optimal solution. And then if the result on the training data is good, as we show here, if the result on the training data is good, then we just see if the result on the training data on the test data is good or not. If the result on the training data is not good, then we have to modify our neural network or modify our loss function or modify the optimization process until we reach good result on the training data. But then we will have another problem is even we have good results on the training data, sometimes the result on the test data is not good. This is a very common problem in deep learning or machine learning. We call overfeeding problem because we where is my over? Because one moment. Okay, because we just follow the training data too much to build a function that is not general enough to handle the test data. So if our model neural network performs good on the training data but not bad on the test data, then we have overfitting problem. Then we have to resolve this overfitting problem. So now we will start to see, okay, how to do this debug process. Okay, so first let's take a look at what if the result on the training data is not good. Then first we need to worry about the activation function. Also we need to worry about the learning rate. The adaptive learning rate, we will discuss it in later lecture. For this introduction course, we talk about the activation function first. Okay, now let's do a practice. Let's load the regression model again. And let me change. Let's load the regression. Go to GitHub. Say leave the original previous one and then run this new one. We already explained this, so I will skip quickly. And then we generate our data, split our data, take a look at the data, and then we build a neural network. Here, instead of using the ReLU as the activation function, instead of using ReLU as the activation function, I change it to sigmoid. I change the activation function to sigmoid. If you want to know more about this ReLU over activation function, you can search for Google by yourself. Okay, but at this moment, You just know it is a activation function applied after we combine, we do the linear combination of previous nodes, then we apply an activation function. Okay, now you see we change the ReLU to sigmoid, and then we use the same loss function and the same gradient descent strategies, and we train for one loop, and then we did the same thing, we train for another 2000. Okay, now here remember this is the loss function we create when we use ReLU. Now let's take a look at the loss function. As you can see here, the neural network does not improve any because the loss function goes from 36 to the 10 to the power 15, reduce only to 28. Actually, we can say it does not reduce it. Okay, only reduce a very little bit. And if we see the performance on the test data, you can see. Okay, the green is the value predicted by the neural network, and the red dot are the true answer. As you can see here, even we train 22,000 times, means we go along the gradient direction by the EDA learning rate for 2,000 times. In the previous version, if we use the ReLU activation function, the neural network already learned. But here, even we train for 2,000 times, the neural network does not learn at all, because you can see the green line are the predict value. So why when we change the activation function from ReLU to sigmoid, why the neural network cannot learn? The problem is due to this vanishing gradient problem. Remember that for the neural network to adjust these parameters to find the optimized loss function, we use gradient descent. And in order to calculate how much we should adjust this weight to make the loss function become small, become toward 0, we use the chain rule to calculate. So for the weight close to the output node, the chain is short. But for the weight far away from the output node, the chain is long. And if suppose this is a small value, this is a small value, then you know two small value multiple will make the gradient even smaller. So when we do backpropagation, calculate the partial derivative from the layers close to the output toward input, our gradient becomes smaller and smaller due to the long multiplication of smaller values. So here the gradients are larger, here the gradient small. Once we have smaller gradient, you know, then the learning process is small because we go with very small value. So smaller gradient, we will have smaller update. So the learning very slow. So after several epochs, here the neural network already, the weight already converge. But here the weight is still very random. So, and then turns out the neural network will not learn. Especially when our loss function is sigmoid, because we will introduce the activation function later in our later lecture note. Here we just simply introduce the sigmoid. The sigmoid activation function is a function goes from 0 to 1. So any larger negative value will become 0, and any larger value will become 1. So even here we have larger value. When this linear combination passes through sigmoid, it will become 0 to 1. And then together with the vanish gradient problem, so we will make this gradient here very, very small. That's why if you use sigmoid, the neural network does not learn. On the other hand, if we use a ReLU activation function. ReLU activation function has this shape. When the value is negative, output 0. When the value is positive, just output itself. So as you can see, if we use ReLU, actually, okay, when the output is 0, we just output 0. When the output is positive, it's itself. So if you take out the node with 0, so if we use ReLU, our neural network actually becomes a thinner linear network. So a linear network with linear combination will not suffer from the gradient too much. So if we use ReLU, we can resolve the vanish gradient problem. That's why when we use ReLU, our neural network can learn. Okay, so that's if you cannot get good result even on the training data, first check your activation function. But as a common practice, right now, usually we just use ReLU as the default activation function. And the second thing to check is we use adaptive learning rate. The learning rate topic we will discuss later in our lecture. Now, one more thing is sometimes we cannot get good result on the training is because the training data we have is sparse. Imagine this problem. Usually the data we collect for our machine learning model is a high dimensional space. Take a look. For example, in this, we have 23 data. Each data has 19 features. Now imagine you are not in a 1 or 2 dimensional space we are already familiar. We are in a 19-dimensional, high-dimensional space. And imagine this data with this value are located very sparsely in this high-dimensional data. So usually we want to train a neural network with a very sparse data, and it's very difficult. So here I provide a simple example. We just use one-dimensional, but okay, it's sparse data. So let's go to open GitHub, and let's open this learn from sparse data 1.2.1. I just leave the previous one and run this new one. Continue. Okay, here I already opened too much notebook, and the Colab only allow me. Okay, so I just finish this and finish all the previous. Okay, now I start. Now it's connecting. Okay, I generate data. This time I try to simulate the sparse sampling problem, so I only generate 40 data, and then use the 80%, 32 data as the training, and 8 data as the test. And the y here I use a cubic function. So I want the neural network to learn this cubic function from only 32 data and be able to predict the value of this test data. So here I build a neural network with only with the same neural network, 30 and 15 in the hidden layer. I use the torch summary to check out how many parameters in my. The parameters means how many weight, how many parameters, how many weight, and how many BIOS. Okay, these are the parameters we want the neural network to learn, the weight and the BIOS. So in total, this neural network has 541. You might calculate manually by yourself. Okay, here if you want to use the torch summary, this means how many data for training. Here you can, because in my case I have 32, so you just actually you can input any number. Later on when we talk about mini batch training, okay, but here you have to put 1 because here we only have 1 features. Here you can put any number. It will tell you, okay, if each batch is 10, then how many RAM you should use. But the number of parameters will not change. Define the same loss function, define the same gradient descent. We use Adam and we use a learning rate. And then we train it for 5,000 times. Okay, so we train this for 5,000 times. Let's go back. Pass-through activation function. Now we, okay, and then take a look at the loss function. As you can see, even we train 5,000 times, the neural network does not learn because the loss function is still very high. Is still 1 or 2 to the power 10 to the power of 22. The loss function. Okay, let's take a look at the the loss function is still very large. See the performance on the training data. The rate means the true. Sorry, I should use the rate. Means the true answer, and the green is the answer predicted by the neural network. As you can see, if we want to learn from sparse data, only 80 data, only 32 data, if we want to build a neural network to learn, then with this small size neural network, it is impossible to learn. So how to improve? Okay, one way to improve, of course, we increase our neural network size to have more parameters. For example, I increased to 100 nodes in the first layers, 100 and then 100 to 50. I increase the number of parameters and trying to see whether my neural network can learn or not. You don't need to run from beginning, okay? So I just run from here, and then remember before we have 541 parameters. Now we have 5,000. Okay, about 10 times. Let's see if it can learn or not. Define the loss function, define the optimizer, and send data from array to tensor and train 5,000 again. Now this time we train the neural network with a more complicated neural network with more parameters. Now we finish training. Let's take a look at the loss function. This time it improves a little bit, okay, but still not very good. Let's take a look. Okay, the loss function is still very large. It's improving. Okay, the rate is close to the green. The the value predicted by the neural network now is close to the true answer. So I have a homework here. Just modify my code, either make a more complicated neural network or training for more epochs, means we go along the gradient direction more times, try to improve this result. I will leave this as a homework. So the first of your homework 3 will be this. Okay, so one problem with this, okay, for example, in this sparse problem, we can create a complicated neural network to learn. Then it performs good on the training data. This green dot will eventually fit the red dot. But then we will have another problem called overfitting, because it performs good on the training data, but then it will perform very bad on the test data because of the training overfitting problem. The thing is, because our model has lots of parameters, so it is able to learn a very complicated function rather than this cubic function. So then it performs good on the training data, but not general enough to perform good on the test data. Okay, let's take a look at this. Let's open my PyTorch code. Okay, go to GitHub and open this overfitting. Just leave the original one and then run this new one, continue to run. Okay, and then generate data. Here, I generate a linear data with some random values. So the idea, we want to learn linear. Okay, we want to learn this general case. Okay, if it's linear, we want to learn this general case, not the specific too complicated function. Okay, so we build a pretty complicated neural network to demonstrate. With this complicated neural network, it may not be able to learn the general function. So rather, instead, it will learn a complicated function. So we will have this overfitting problem. We expect this model performs pretty well on the training data, but then bad on the test data. So our model has 5,000 parameters. Define the loss, define the optimizer, and then send data to tensor and train it for 500 times. Let's train it for 1,000 times. And take a look at the loss function. So as you can see, the loss function is already reduced to close to 0. Let's take a look at the model performance on the training data. As you can see, it performs, this red line is the whitehead. Oh, sorry. This red line is whitehead, and the green dot is the value predicted by our model. And let's take a look at the test case. As you can see, the loss function for the test, the mean square error is much larger than the training data. It's a typical indication of overfitting, as you can see. Let's see, the red line is head, green is the value predicted. Okay, as you can see, okay, it performs good on the training data but bad on the test data. It is a very typical problem in machine learning or deep learning. Here we have this overfitting problem. Okay, now you have to know how to overcome this overfitting problem. So before we explain how to overcome this overfitting problem, the second part of your homework is to modify this code and change the linear equation to quadratic or cubic, like here, like this. Change the training data to quadratic and try to create an overfitting situation using this quadratic or cubic function like this. Okay, so we define our training data as a quadratic or cubic function, and then we define our complicated neural network. It learns very complicated function. So it will perform good on the training data, but then performs very bad on the test data. Okay, that's your second part of your homework. Okay, in the Hongyi's lecture, he also mentioned this. As you can see, as the model number of parameters increase, the training performance improves, but then the test performance become bad. Okay. And also in the Hongyi's lecture, if you see the bad performance on testing data, okay, for example, if we have a deep neural network with more parameters and performs bad on the test data, it may not be overfitting problem. We need to go back to check. The Hongyi just mentioned a case where even the complicated model performs bad on the training data. So it's not the overfitting problem. It's the problem that we don't have a good neural network structure or a good optimization strategy. So even the complicated neural network does not perform well on the training data. Okay, now let's go back to the overfitting problem. There are three ways to resolve the overfitting problem: early stopping, regularization, and dropout. Okay, let's take a look at the early stop first. Okay, the early stop means we watch the performance on the training data and the test data. If the performance on the training data increase, the loss reduce, but the loss function of the test data increase, then we know we will start to have the overfitting problem. Then we should stop our training here. Okay, usually we do not use test data. We split a portion of data from the training data as the validation data. So here I provide a PyTorch exercise to do this early stop. Let's go to open GitHub and open this early stop. Yes, I want to leave and open a new one and then continue to run. Okay, I have to remove. Okay. Okay. Continue to run. Connecting. Initialize again. Check for my. Okay. Generate data. Okay. Split my data. So here I split my data. First 80% to training and 20% to test. And then for the training data, I split 80% to the training and 20% to the validation data. So the training data is shown in blue, validation data is shown in green, and test data is shown in red. Okay, now I built a neural network. Okay, and since I built a neural network with 5,000 parameters, and I want to learn basically is a linear model. So I can expect we will have overfitting problem. Means it will learn a complicated function that performs very well on the training data, but then bad on the test data. So now this time I will use early stop to train. Loss function optimizer. Okay, so first I convert my training data and the validation data, training data and the validation data into tensor, and then I perform the training epochs. Okay, but I watch the performance. I watch the loss of both the training and the validation. If the loss of the validation starts to increase for 2 consecutive times, then I will stop the training because I found I might start to have overfitting. So the idea is like this. Okay, so now I start the training. At each epoch, I watch the validation loss. If the validation loss increase for 2 consecutive times, then I will stop the training and call it early stop. Now I start my training. Okay, now stop. Okay, take a look. Okay, here the green line is the validation loss and the blue line is the training. As you can see, okay, in this case it's not good. Both the training and the validation start to increase. In my previous example, okay, I show you is very similar to Li Hongyi's PPT, the training data. And okay, let me try it again. Okay, let me try it again. I generate the data again because here I use random variable to split again, take a look, okay, and build my neural network. Define the loss function. Actually, I don't need that much. Okay. Okay, now stop, take a look. Not good. Okay. Anyway, you might run this by yourself. Anyway, the idea, yeah, I don't know, for this time, both the training and the validation increase. Okay, let's take a see. The training data performance is not good. Okay, let's take a look at it's even worse on the test data. The training data loss is 6,000. The test data is even more. So we did not solve the overfitting problem using early stop in this case. Hey, I don't know. You might run this several times. Okay. I think it's because I randomly generate the data and randomly split. Maybe the training and validation data here I generate randomly is not good. Okay, I don't want to run it again. I just leave it to you. Okay, you can run the program. Yesterday when I run this, here the loss function is very similar to here. The training loss start to still decrease, but the validation loss start to increase. Okay, that's called early stop. That's one of the way to overcome overfitting. And then I want you to practice this again based on your homework 3. Remember, in homework 3, we change the linear equation to quadratic or cubic. The second way to overcome this overfitting we use a lot in machine learning is called regularization. The idea of regularization is to modify the loss function to add a regularization item. Here if we use the L2 regularization, means after the original loss function, which measures the mean square error between the true answer and the predict error, we add the regularization term, that is the summation of the L2 norm, means the square of. Okay, so by adding this L2 regularization, as you can expect, if we want to minimize the loss function, we will try to the gradient descent optimization will try to reduce the weight. Okay, so if we have smaller weight, then smaller weight will be easier to handle the overfitting problem. For details, you might take a look at Li Hongyi's video or any video that explains L2 regularization. Okay, if you take the derivative of this partial derivative of this new loss function versus the weight, you can see if we put L2 regularization actually in the gradient descent, we are doing a weight decay. So if you want to do L2 regularization in PyTorch, it's very simple. You just let's open this L2 regularization. Leave and run. Continue. If you want to do L2 regularization, or let's continue. What you did, you just add a weight decay in your optimization function, because if you take the partial derivative of your new loss function, you can see here this is the original item, because these two are small, because this eta is the learning rate, and this gamma is the weight of this L2 regularization. This item is small, so this is close to 1, and as you can see here, we just take the weight decay. Okay, instead of taking, we just anytime we decay the weight a little bit. If here is 1, then it's normal gradient descent. So if we add a L2 regularization, we just anytime we do the gradient descent, we reduce the weight a little bit. So it's called weight decay. And if you want to do L2 regularization, just say here how much we want to do weight decay. That's the lambda value. Okay, for example, here I put 0.01, and then send to tensor, train 500 times. Take a look at the loss function. So performs pretty good on the training data. Take a look at the test data. It's about the same. Okay, so applying L2 regularization, we can make the performance on the test data similar to the performance on the training data. Of course, here is not that good. Why? Because in the neural network, the weight of the neural network when we start the neural network, the weight is already small. So even here we decay the weight every iteration. Actually, we did not improve too much. But for other machine learning algorithms like linear regression, L1 and L2 regularization really helps overcome the overfitting problem like the lasso and the ridge. Okay. And then similarly, I want to use cubic or quadratic case to try L2 regularization. And for L1 regularization is similar to L2 regularization, except the loss function, we add the summation of the absolute value rather than square. And then if you take the partial derivative, you see this is the normal. And then every time we times this eta is learning rate, and this lambda is the L1, the coefficient of L1 regularization, and times the sign, either positive or okay, negative. And then here, so this item is the regular, and then we minus another one. Okay, so compare the L1 and L2 regularization. L2 regularization, every time we decrease the weight from 1 to 1 minus eta times with a small value. And L2 regularization here is still 1, but here we decrease the value. So let's take a look at the L1 regularization. Go to GitHub. Run, continue. Have to too many sessions. I have to finish all the previous session, rerun it again, because Colab only allow a limited number of sessions. It's free. Okay, so it's understandable. Then generate data, split, and build the neural network. Okay, takes a while. And for L1 regularization, for L2 regularization, because it's weight decay, so we define it in the optimization. Here I just show you the layers name. Here the layer 0, 1, 2, 3, 4, and it's weight in the BIOS. We have about 5,000. So for L1 regularization, we just define an optimizer without weight decay. And then during training, every time, this lambda, not 10, 0.01. During training, every time when we calculate the regular loss function, when we calculate the regular mean square error, we add L1 regularization. So the loss is loss times lambda times the L1 regularization. Lambda times the absolute value of our parameters. So here we search for the neural network layers if it's weight. By the way, usually the regularization applied to weight. We will not apply the regularization to BIOS. Okay, otherwise the whole neural network will output a very small value. So we check for the node. If the node is weight, then we apply regularization. So now we train for 500 times. Take a look at the loss function. Okay, take a look at training performance. Okay, now take a look at the test performance. Oh, in this case, unfortunately, we have overfitting problem. It might, when I practice at home, okay, it's okay. But here, as you can see, the loss function for the test data is dramatically larger than the training data. So L1 regularization does not work in this case. Okay, so I want you to do this as a homework to see L1 regularization whether the L1 regularization works on the cubic or quadratic training data. And finally, just as we mentioned, for other machine learning, like linear regression, the L1, L2 regularization works pretty well to overcome the overfitting problem. But as you can see here, for neural network, the regularization does not perform pretty good because the neural network, we already initialize our weight with a small value. Let's take a look at the PyTorch demo. So we open my PyTorch code. Initial small weight. Leave the previous one. Run. Continue. Import PyTorch. Check for GPU. Generate data. Build the neural network. Now, I take a look at the initial values of this neural network. As you can see here, okay, the default neural network, the weights and the BIOS are already small, but we can make it even smaller. Okay, here I just manually assign my initial weight to be mean 0 and standard deviation 0.2 to make the initial value smaller. As you can see, okay, I make the initial value smaller. With this small initial value, actually I might not need to do regularization. So I just use the regular training process without any regularization to train my neural network. Take a look at the loss. Okay, here's the training data performance. Let's take a look at the test data performance. 705. I still leave larger. Somehow today when I demo this, okay, it's not very good, but as you can see, we still have some overfitting problem, but not very severe. So for neural network, we can just assign our initial weight with very small. But if you want to assign even smaller, you can make the standard deviation even smaller. Okay, now let's take here. Li Hongyi just mentioned if you have using regularization, you can successfully reduce the overfitting problem. Okay, now we already explained how to use early stop and regularization to overcome the overfitting problem. Okay, now let's take a break and we will talk about dropout.